Okay, welcome to 3.03. Now, this one is probably going to be a little bit longer than your average one. You can see at the top, we've got 12 pages to go through. Now, the good news is if you, paid any attention in the third quarter, about 80% of this stuff is repeated. It's not new, but the last couple pages are a little new. I don't think we've talked about those before, but for the most part, you will have seen a lot of this, and hopefully it comes back to you and makes it pretty easy. Okay, so all of this stuff we kind of did over the period of a week or 2 weeks, but they cram it all into one section for you to do. So we're going to talk about transformations, which talks about translations, which is sliding, rotations, which is flipping, and reflections. No, rotations, which is turning, and reflections, which is flipping. So we'll talk about all those things. Just a reminder, when you transform from your original shape, the original shape will be labeled A, B, and C as their points. And then the new shape, the one after you transform it, will be labeled A prime, B prime, and C prime. Okay, we've done that before. You'll see it when we get to an example. So a translation. Now keep in mind, translation is one type of transformation. A translation is simply just a slide. So if you look at your triangle here, you can slide this triangle up or down, and of course left or right. And that is a translation. It's simply a slide around. Now, we don't ever really slide it diagonally. You can see that right now it looks like it's been slid diagonally. However, it's actually a result of two slides. Remember, we originally we originally slid it down and then we slid it to the right. So two slides to create kind of that diagonal slide, but ultimately it was two things we did, a down and an over. Okay. Now keep in mind that the slide does not change the shape at all. It's still the exact same size, the exact same shape. It didn't get any bigger or any smaller, anything like that. It just simply slid, kind of like moving a pencil around on your desk. It doesn't change its size, nothing like that. It just moves. Okay. And that's what talks about here. Now, of course, on a coordinate plane, you can see these slides. Now, let me see if I can illustrate this a little bit better for you. All right, let's zoom in. So here on this graph, you can see the original one was this top one. I know that this is the original because it's labeled A, B, and C. This one here is the new one because it's labeled A prime, B prime, and C prime. So that's how you can tell the difference between the original one and the one that was moved afterwards. Now, this is a slide, as you can see, because it doesn't change its shape at all. You can tell that it's been moved from here to here. It moved down and a little over. Now, if you look at it, let's look at just one particular point. Let's go from A to A prime, right? How do we get to that shift? Well, let's consider the left and right movement first. So to get from A to A prime, we would have to move the point over 1 unit, right? Have to go 1 unit to the right, going from 3 to 4, if you think about it on the x-axis, right? And then if we want to get from A to A prime in terms of going the other direction, we would have to go down 3 units. So down 3 being a minus 3, because you're going from 6 up here down to 3 here, right? So you have to go down 3 units from 6 to 3. So we have +1 in terms of moving to the right. And then we have -3 in terms of moving down. And so those are the two translations to get this shape moved. So how you would write this out is you would say, as a rule, you would write x, y, translate it to x plus 1 and y minus 3. So you're putting the +1 in here because, excuse me, as we mentioned, the x-axis, which moves left or right, went to the right 1. So right 1 is the indication of the +1 here. And you see the -3, of course, for the same reason, because the y-axis, which goes up or down, the y-axis went down 3. So that's to indicate down 3. The other way you could write this, but I don't think they show it in here, is you could simply write the translation as one of these pointy brackets, 1 and -3. That says the same thing as what we saw down there. You know, there we go. Looks a little nicer, right? It says the same thing. It's still saying +1 for the x and then -3 for the y. But I think for the most part, they're going to write it like the way I wrote it the first time. So just something to kind of be reminded of. And you can see they draw that illustration there. And if you look at it on this graph in front of you, you can see that the point from B to B prime does the same thing. And from C to C prime, it does the same thing, which is go right 1 and down 3. Every single point moved right 1 and down 3. We just used A to A prime to find it originally. But it's the exact same thing regardless for the B and B prime and the C and C prime. Another thing to keep in mind is we call the original triangle the pre-image because it's what happens pre-translation. And then we call the moved one just regular image, not post-image or anything, just the regular image. That's what happens after the translation. So just something, again, terminology to keep in mind. All right, so look at this example. We want to follow the rule of xy to x minus 4, y minus 7. All right, so if we do that, let me go ahead and be able to write on this. If we do that, or follow the rule of xy translated to or changed to x minus 4, y minus 7, let me just double check that was correct again. Oops, wrong thing. Yeah, x minus 4, y minus 7. Then for each of these points, let's just start maybe with the r, right? We are going to go, according to this, down 4. Or I'm sorry, not down, because x is a left and right. That always messes me up. We have to go left to right first. So x minus 4, remember, is your left to right. So minus 4 would mean left 4, because you'd be going this direction. And then the minus 7 here would indicate going down 7. So keep that in mind. It's opposite from how I normally think of it, but the x value refers to the x-axis, which is why it's, you're focusing on going left or right. A minus sign would go to the left since negatives are to the left, and a plus sign would indicate going to the right. Obviously, since ours is minus, it means go to the left. So let's focus on r. Let's go to the left 4, so 1, 2, 3, 4. And then also consider going down 7 for the y minus 7. So going down 7, 1, 2, 3, 4, 5, 6, 7. And we end up there at -1, -6. So this is what we'll call r prime. We do the same thing for e. So go to the left 4, 1, 2, 3, 4, and then down 7. 1, 2, 3, 4, 5, 6, 7. That puts us right here at 1, -6. And we'll call that E prime. And if you do this for every single point, going to the left 4 and then going down 7, you'll see that we create the exact same shape. This is where T prime will go. This is where, is that an A? I think, yeah, that's where an A prime will go. This is where the W prime will go. And here's where the S prime will go. And it will create the same shape, just moved, obviously, to the left 4 and then down 7. And the other way you can think of it is by writing out the actual ordered pairs. So let me switch to white here so I can write in the margin. The ordered pair for R is 3, 1. If you follow the rule of x minus 4, y minus 7, then subtract 4 from the x value, so 3 minus 4 will become -1, and subtract 7 from the y value, 1 minus 7 would be -6. And this is where r to r prime would be. And of course, if you look at our paper, r prime was indeed at that point, right? -1, -6. And this goes for obviously all of the points. If you look at E was originally at 5, 1. 5, 1. But if you follow the rule of subtracting 4 from the x, which 5 minus 4 would end up being 1, and subtracting 7 from the y minus 7 would be negative 6, you end up here, which again, if you look at the graph, 1, negative 6 is exactly where E prime ended up being. So that goes for obviously all the points. I'm not going to write them all down just to save time, but that's how it works. And you can see that's what they did here. They show you all those points. I obviously showed you how to do with R to get to -1, -6. And I also did it with E to get you 1, -6. But that obviously you can see for all the other points, they've done the same thing. And they've got that graph to show for it. And of course, you could just do what we did originally, which is count left 4 units and down 7 units to make it work out. So if we practice just one of these, let's move this pentagon. It wants to move it x minus 5, y plus 4. So let's try this one out. X minus 5, y plus 4 is our rule. So x minus 5, y plus 4. So if we follow that rule, then x minus 5 means left 5. Remember the x-axis goes either left or right. And since it's minus, we're moving left. And then y plus 4 means up 4. So let's start with G, just because. And let's go left 5. So 1, 2, 3, 4, 5. And then up 4 as well. 1, 2, 3, 4. And that's where we will find G prime. Do it for H. We go left 5. 1, 2, 3, 4, 5. And then up 4. And we end up here for H prime. If you do it for I, J, and F, I will move you to here, J will move you to here, and F will move you to, I'm trying to count this out, here. So this would be I prime, J prime, and F prime. So our shape would look like this. So it's the exact same shape, of course, just through counting. Now, if you want to write out the ordered pairs again, you could do that. So just to show you with the first couple points, remember, if you look at where G started at the point 1, -4. But if you look at G prime, you remember you'd have to go, it's x minus 5 and y plus 4. So the x value, I would subtract 5. So 1 minus 5 would be -4. So that's where G prime would be. And then the y value, add 4. So -4 plus 4 would be 0. So it would be at the point -4, 0. And again, if you look at where I put G prime, there it is at -4, 0. And that works for all of the points. Just to show you one more with H. H originally started at 3, -6. And if you subtract 5 from the x value, you'd end up at -2. If you add 4 to the y value, you'd end up at -2. So -2, -2 is H prime. Again, if you look at our graph, -2, -2 is exactly where H prime was. That goes again, same thing for I, J, F, but I'll save you the time. I won't work it out here. Just kind of show you, but it works the same way on all 5 points. All right, so that seems to be translations. I think next up is reflections. So reflections are very simple. It's just a flip over the graph. You can kind of see how our original picture here at the top flips over and we have kind of a mirror image. It's very important that you recognize the fact that it's a mirror image. It's not like a translation where it's just a slide to the bottom. You're actually flipping it over, right? It's upside down now. So that's what a reflection will look like. Now we've done these in class. We've written rules for these as well, and we're going to have the same rules again. So a reflection over the x-axis means that obviously you take something from the top of the x-axis or the bottom of the x-axis and you flip it to the other side. So in the one that you see on your screen, this one started on the bottom because you can see the A, B, C, and D, and on top it goes A prime, B prime, C prime, and D prime. right? So this one at the bottom was the original one. It's being reflected over the x-axis. So the x-axis is this line, and we're reflecting a mirror image of it onto that side. And so you can see it flips over, becomes upside down over the x-axis. Obviously, if you reverse it over the y-axis, which is not in this example, but in a future example, a reflection over the y-axis will flip it over this way, right? And I'm sure we'll see an example of that in a second. This just shows you a couple different graphs. Again, you can see how it goes from the bottom up to the top. It just reflects over again and again and again. Just a couple different examples there to illustrate your point. Of course, obviously, if it reflects over the y-axis, it does the same thing, just does it sideways over the y-axis. But the main thing here is, what if you notice, if you look at the points on these, right? If you notice these points, I'll use this one to illustrate. This is, of course, reflecting over the y-axis. C goes to C prime, right? So that's the original point, that's the new point. It started as -3, -2, and then when it flipped, it became +3, -2. So notice how similar but different they are. And let's look at B and B prime. So B started at -6, -3, but it ended at +6, -3, right? So again, notice how similar but different they are. Same thing with A. A starts at -6, -5, but it ends A prime at +6, -5. So you might notice a pattern here. The pattern being that the x value is changing its sign from a negative to a positive, -6 to a +6, -6 to a +6 there. But the y values don't change in sign, right? The y value stayed -2 and -2, stayed -3, -3, -5, -5. This is reflecting over the y-axis. You'll notice a similar but different one when you reflect over the x-axis. So when you reflect over the x-axis, if we look at this example, again, notice from A to A prime. So from A, which was -7, -4, to A prime, it goes from -7 to +4, right? So again, notice how similar but different they are. If you look at D, -4, -4, when you reflect it to D prime, you end up at -4, +4. So without doing too much, you can already kind of see the pattern. The x value is not changing on this one. It's staying the same, -4, -4, -7, -7. But the y value is changing, right? It started as a -4, then went to a +4. With D, it started at -4 and then went to a +4. So this is where we create our rules from. And then we have the same thing for reflecting a line over y equals x. So that's just a diagonal. So when you look at this one, again, just look at the points and you can kind of see the rule for yourself. So let's start with A. You have -4, +3, but when you reflect it over this diagonal, the new A becomes 3, -4. If you look at C, for example, it starts at -2, 5, but when you reflect it, C prime ends up being 5, -2. So notice what's happening. The x value for A was -4, but then became 3, whereas the y value, the y value, oh man, hold on, trying to make sure I use the right tool. The y value was 3, and then it changed into -4. Now, you'll see I highlighted this for a reason. What's happened here is actually the x and the y value are swapping. The x here was -4, but then the y here became -4. The y value here was 3, but then the x value became 3. So the x and the y are essentially just switching places from over this reflection. You can see that here. The -2 was x, the 5 was y, but when we flipped it over this diagonal, it switched the other way around. The 5 was the x and the y was the -2. So that reflection is just a switch in the x and the y. So to create a simple shortcut for you and something maybe you want to write down, okay, this is from previous ones, okay, rules. This one will be for reflections. So if you flip over the x-axis, your rule is xy change to x-axis was, if we go back and we look, go back to reflecting the x-axis, this was same x but opposite y. So it would go to x negative y would be the rule. If you flip over the y-axis, our rule was our point changed to negative x positive y. So it was the opposite x but the same y. And then when we reflect across y equals x, we had the rule where they just flipped around. They switched from xy to yx. The points reversed. We've done this in the past. This is not new to you. We've talked about those same rules before. We're also going to do them again. So that's for reflections. I believe next step is going to be rotations. So rotations, of course, is when we turn the diagram. So you can see it's not changing its shape at all, but it's just turning left, right, or whatever. Now, you'll notice when you go a quarter of the way around, that's a 90-degree turn. If you go the complete opposite direction, it's a 180-degree turn. Now, notice the difference between a 180-degree turn and a flip. If it was flipped, these would look like a mirror image of each other. But it's not a mirror image of each other because this, it still retains that same exact shape, just turned all the way around. And then you have 270-degree turn, and then, of course, back to the beginning where it'd be 360-degree turn. And we're going to have examples and rules for this as well. So when you turn it 90 degrees clockwise, let's look at this one, and then we'll make our rule. So 90 degrees clockwise, let's look at A, starting at 3, 3. 90-degree clockwise is turning it 90 degrees in the clockwise direction. A prime ends up being here at 3, negative 3. So let's pay attention to what the rule is that we're doing. If we look at B prime, B to B prime, it starts at 1, 2, and then it switches to 2, negative 1. All right, so let me write this down a little bit neater so that we can kind of better see these points next to each other. So remember, A was 3, 3, A prime becomes 3, negative 3. B was 1, 2, but B prime became 2, negative 1. And then C was 4, 1. C prime becomes 1, negative 4. So let's see if we can figure out a rule for this. It's hard to tell when you look at the A to A prime because the 3's are both the same. But if you look at B and C here, you have 1, 2, switches to 2, negative 1. So the xy of B, what was x was 1 is now the y, and it's the opposite sign. So what was the x value is now y, and it's opposite. So this would be opposite of x for the new y value. The original y value was 2, and it's still 2 here, but it's the x value instead. So the y switches to become the x value. So our rule is xy changes into y negative x. So that means the original y value will now be the x value, and the original x term will change its sign and become the new y value. And you can see that's done for C as well. For 1, 4 is the original x value, 1 is the original y value, but following this rule, the y value will become the new x, so the 1 here becomes the new x, and then the x value will change its sign and become y. So the x value is 4, we're going to change it to a negative 4, and it's now the y value. And that's exactly what was there. Right? So our rule, like I said, is xy changes to y negative x. Let's add that to our rule list. Xy changes to y negative x. So this is for rotations. You should also make a rule list like this as well. So this is 90 degrees clockwise. We had x, y changed to y negative x was our rule. Let's look at the next rotation. 90 degrees counterclockwise. So let's write down these points. We had A at 3, 3, and then A prime went to negative 3, 3. Again, that's kind of hard to tell because they're both 3s. The B was at 1, 2. And now B prime is at negative 2, 1. And then C was at 4, 1. And C prime became negative 1, 4. So let's see if we can write the rule for this. So xy, the original xy turned into what? Let's look at B and C since A is kind of kind of complicated because they're both 3s. The x value was 1 is now the y value. So what the original x value is now become the y value. So the original x value is now the y value of the new points. The original y value changes its sign and becomes the x value. So the original y value will change its sign and be the new x value. So our rule looks to be negative yx. So let's apply that to C to make sure that it fits, right? So C was originally 4, 1. If we follow the rule, we're going to change the sign of the y value and put it in the x place. So change the sign of the y value to a negative 1 and put it in the x place. The x value is going to stay exactly the same, but become the new y value. So the x value is 4. It's going to stay as 4, but become the new y value, negative 1, 4. And that's what it was, right? So that rule is good. We've written it down correctly. So the rule is xy changed to negative yx. So xy changed to negative yx. Now, what type of that was 90 degrees counterclockwise, right? 90 degrees counterclockwise. All right, and then 180-degree rotation. I'll cut you the explanation for this. The rule is very simple, though. If you look at it there, it's just the original values just become negative. They don't switch around. Like if you look at B from 1, 2 to B prime becomes negative 1, negative 2. It's still 1, 2. It's just both signs are opposite. So the rule quickly for 180 degrees. Now, obviously, 180 degrees clockwise is the same as 180 degrees counterclockwise, so I won't specify that. But it simply changes to the opposite of x, the opposite of y, but the x is still the first part, the y is still the second part. It's just you change the signs. So those are your rotations. Now, just a side note, I don't know if they mentioned this, but we'll go ahead and add this. 90 degrees clockwise is the exact same as 270 degrees 270 degrees counterclockwise, and 90 degrees counterclockwise is actually the same as 270 degrees clockwise. So just something to remember is that those are the same rules would apply to those two. Okay. Zoom back out. There we go. Okay, so again, know your rules. If you want to go rotating it clockwise 90 degrees, you have the rule for rotating it clockwise 90 degrees, like we've written down. Hopefully you've written it down. XY translates to Y negative X. That's obviously written right here. But just like I said, you want to make sure you have these written down. I'm not going to go through this example. You guys can kind of see it laid out. But you would take the points and switch them around. I think there might be a better example coming up. Let's see. Okay, so symmetry. This is the part that's kind of new to us. Symmetry is pretty easy to understand, but trickier to apply. So obviously, you know what symmetry is. It's basically a line where you can cut the figure directly in half, and the either side is the exact same, the left or the right side or the top or the bottom, whatever. They both are essentially mirror images of each other, right? So if we look at the 3 diagrams here and we try to imagine a line of symmetry, how many lines of symmetry would this triangle have? So first, an obvious one is right here. That's one line of symmetry that splits it down the middle from left and right. But there's more. You can draw the line this way, and you can see that sort of the top and the bottom are again symmetrical. So that's 2 lines of symmetry. Let's keep a tally here. 1, 2. There's also a third line of symmetry right here that cuts the triangle directly in half. Okay, assuming you can do better. So that's 3 lines of symmetry. Now, I don't think I can find any other lines of symmetry because obviously if I do it like this, the left side and the right side here are clearly not symmetrical. So 3 is the most I can think of for our triangle. Let's look at this picture, the middle one. I can tell a line of symmetry here down the middle. That splits the top and bottom right in half, and it looks even. They're both pretty much the same image, so that's 1 line of symmetry. I also know I can do it top and bottom. So the left side mirrors the right side. Those are symmetrical as well, so that's 2 lines of symmetry. If I do it diagonal, though, I'm not having a mirror image because this does not reflect over here. Because if it did, the green part would lie here and the blue part would lie here. It would be a mirror image, but it's not a mirror image. So it's not symmetrical diagonally. And so I think the only symmetry we can have there are those 2 lines. And then the last one is pretty tricky. There's a lot here. You can do one here, so that's 1. You can do another this way, so that's 2. You can also do one diagonally, because diagonally that is a mirror image from the left and right side. So that's 3. You can also do this diagonal, so that's 4. I don't know if there's any more to that. I think it's 4, but let's check this, see if I missed any. 1. I think we got them. I think we did them all correctly. It doesn't say it, but you can see those lines are the same lines that I was drawing. So we're good. So that's something to keep in mind when we're looking at our transformations, is that they should still have the same lines of symmetry. Now, is this the part where it gets more interesting? Yes. So rotational symmetry. So this is happening when you turn something. Now, if you look at this helm, okay, or as I like to call it, the steering wheel of a ship, right? If you turn it, how many times will it become the exact same shape? So let's turn it just 1 turn, not full rotation, but let's turn it 1 time. Turn it 1 time, there, right there, it's the exact same shape again, right? So that's 1 turn around. We had this peg went from here to here, right? If I turn it again, right, that's 2 turns. We've gotten from this peg goes to here now. So, and it's the same shape, so that's 2 turns, right? Let's do it again. That's 3 turns. 4 turns. We had the original peg is now down here. That's 4 turns. 5. So we're at this peg now. And it's the same image. 6. 7. And then all the way around 360 makes 8. Where our peg returns back to the original position. So there are 8, basically 8 symmetrical parts. If you turn it 360 degrees, it becomes the same image 8 times over. So why is that important? Well, there's something we like to find called the angle of rotation. So since we can turn the ship's wheel 8 different times in the span of 360 degrees, a simple way of calculating the angle of rotation is taking the 360 degrees, dividing it by 8. And when you do that, 360 divided by 8 becomes 45 degrees, meaning that if you turn the wheel 45 degrees, that creates the exact same image again. So that's a 45-degree rotation to go from one image to the next. So that's your angle of rotation. That's why our symmetry becomes very important. So remember how we got that, right? We knew that there were, we counted there were 8 times, and obviously the shortcut here is count the pegs. 1, 2, 3, 4, 5, 6, 7, 8. 8 pegs obviously means that when you turn it, you can have 8 different, I guess, images, right? That's kind of the shortcut, right? 360 degrees divided by 8 gets you the 45-degree rotational angle of rotation. All right, how many lines of symmetry can be found? I'll let you guys kind of guess on these and then check your answer. So you have image 1, image 2, and image, well, this isn't image 3, but for this practice. So a decagon, just by the way, a decagon has 10 angles, okay? 10 angles, 10 sides. So the angle of rotation would be found by taking the 360 degrees, because obviously we know it goes all the way 360 degrees around, and dividing it by 10. If it has 10 sides, 10 angles, you divide it by 10. So 360 divided by 10 is going to get you your answer here, which will be 36-degree angle of rotation. So if it was a pentagon and it was only 5 sides, you'd do 360 divided by 5. If it was an octagon, then you would divide it by 8. 360 divided by 8, and so on, right? You get the point. All right, so here are just some practice problems. It goes through everything, so let's try maybe a couple of them. So for this first one, let me screen snippets, and then we'll look at it, right? We have our crazy looking shape, and it says that it's going to be rotated 90 degrees clockwise. So let's go find our rule that we wrote down on our cheat sheet. So 90 degrees clockwise is here, right? XY switches to Y negative X. So XY will switch to Y negative X. So let's follow this rule. Now it's only asking, given all these points, it's only asking the point of G prime. So how will G turn? So G starts at the ordered pair. If we look at the ordered pair of G prime, or regular G, it starts at negative 5, 1, right? Negative 5, 1 is the point there. So negative 5, 1. So if we follow the rule, we're going to write the y term first, not change its sign, just leave it the way it is, but make the y value the x value. So the y value here is 1, so it's now going to be the x value. And then here, negative x means change the sign of the x value and write it as a y. So the x value was negative 5, but the negative x means change its sign, so it's now going to become a positive 5 that we write as our new y value. So there you go. Point is 1, 5. And we should be able to check our answer on that. We don't have to do any of the other points. Like I said, it only asked for that one. There you go, right? 1, 5. It has a whole picture, but yeah. G prime, it only wanted the answer to that one. All right, so what rotation can you see here? Now, it is a rotation, keep in mind, right? It tells you a rotation. So if rotation is it's turned. How many degrees did it turn? Well, it went to the complete opposite side. I'm sure you guys can probably figure this out. But it started here and ended up here. So it turned, essentially, if you base it on an axis, it turned 180 degrees. If you go like S at the origin to S prime, you see it makes a straight line. A straight line angle, of course, is 180 degrees. Either clockwise or counterclockwise, it doesn't matter. It's 180 degrees regardless. So that one should be 180 degrees. You can see they found it through a different means. They wrote the points down and then kind of compared it to, hey, look, we see the points. What rule do those points follow? And they figured the points follow that rule. So it was 180 degrees. But you should be able to look at it through just looking at the picture. All right, so this one is rotated 270 degrees counterclockwise. It wants the coordinates of the endpoints for y, z in the image. Okay, or for our case, it'll be y prime, z prime. So 270 degrees. Let's go ahead and let me snip this and we'll work it out real quick. So 270 degrees clockwise. Now go back to my rules. 270 degrees clockwise is the same as 90 degrees counterclockwise. So we're going to follow this rule here. XY translates to negative YX. So let's write that down. So XY translates to negative yx. Now we're focusing on yz. So yz is here. So let's write down the ordered pairs. So y is at the point 7, negative 1. And z is at 7, positive 2. So if we apply the rule here of changing the sign of y and then keeping x, this would become a positive 1, 7, because the y value, we're changing the sign of the y value and writing in the x place. We're changing this to a positive and writing in the x place. And then the x value stays the same, just becomes y. So what x was 7, so it stays at 7, but just as the y value. If we apply the same thing to z, z will become negative 2, 7. So this would be the endpoints for y. So this would be y prime. This would be the endpoint for z prime. And I believe that's all the question's asking for. It's what are those endpoints? So it should be those 2 points, 1, 7 and negative 2, 7. So let's go back. Let's check our answer. Yeah, 1, 7 and negative 2, 7. Perfect. Right, so just follow the rules. Hopefully you've written them all down. How many lines of symmetry can be found? I'll leave you guys that one. Again, asks, what's the order of rotation? So notice the tips here. There are 5 points. Okay, so in order to find it's not asking for angle of rotation, it's asking for order of rotation. So yeah, since there are 5 points, it is just 5, it's the order of rotation. But if you wanted to find the angle of rotation, you would take 360 and divide it by 5 to get the angle of rotation, which I believe would be 72 degrees. But it's not asking for that, so don't worry about it. Angle, again, here's a go. Angle of rotation for a regular dodecagon. Dodecagon, is that 12 sides? I forget. Yeah, dodecagon has 12 sides. So you just take 360 and divide it by 12, as we mentioned earlier. And then what sequence of transformations will carry ABC to A prime, B prime, C prime? So it looks like that this one simply just turned. So let me illustrate on this real quick. It looks like it's just a rotation, but let's check A. Yeah, from A to A prime, it looks like it just turned this way. From B to B prime, looks like again it turned. And from C to C prime, looks like again it turned. Obviously, it could go either way, so it looks like it's turned 180 degrees to me. And one way, if you can't figure it out by looking at it, is by writing down the points. That would help. So A starts at negative 3, 0. B starts at negative 2, positive 2. And then C starts at negative 1, 0. And then they all change. A prime becomes 3, 0. B prime becomes 2, negative 2. And then C prime becomes 1, 0. So if you just follow the rule and try to figure out which rule it is, it seems like they're just changing the x value to changing its sign, but keeping the y value the same, right? Because this x value changes to a positive. Oh, well, it's not keeping the y value the same. The y value is changing its sign as well. 2 changes to negative 2. So it seems like the original x and y change into just changing the sign of them. So changing the sign of the x and changing the sign of y. So it seems to be following this rule. So if you want to look, you can go back to your rule book and see which one has that. XY change to negative x, negative y. And it's, of course, the 180-degree turn that I assumed it was by the picture. But you can always write down the actual points, write down the rule, and then see which rule you're looking at. So since I can see the rule was xy to negative x, negative y, I would go back through my list here. Oops, zoom back out. I'd go back through my list here and see which one is that rule. Obviously, it's the 180-degree one. All right, that's it. Hopefully you guys do well on the quiz. Let me know if you have any questions. I'll see you guys next one.